Alright, so when it comes to solving limits algebraically, um, rather than using a graph or using a chart, uh, the first strategy we usually think of is the idea of direct substitution, or saying where you have a limit where x approaches some number c for f of x. You set it equal to f of c. So you don't do this anymore. All you do is you just input the c into the function and assume that they both have the same output, L, right? So some curve where this is c, this is L. Yes, this could be the case, but we know that this may not always be the case. For example, maybe it's undefined at that point, right? Then you don't have an L. It's undefined. You can't do that. But there's also a case where sometimes when you plug in your C and you get an output, that output is not necessarily a real number. For example, 2 over 0. That is not a real number, right? So what do we do in these cases? Because we know, for example, cases like this, the function might be undefined at a point, right? But the limit might still be defined. So this is where we need to add a new tool to our toolbox when it comes to solving limits, right? Rather than direct substitution, we're going to use the idea of factoring. And I'm going to use some examples to help explain why this is necessary and why direct substitution is almost always useful but not always useful. So in those cases, we might resort to something like factoring. So this first example says the limit as x approaches 2 for x squared plus 4x minus 12 over x squared minus 2x equals our answer. And let's say I want to try direct substitution, okay? Because assuming I don't know any other method, and I know that direct substitution is very, very often the right choice. So let's just try it first. So I'm just going to plug in 2 into this function, and I'm going to get 2 squared plus 4 times 2 minus 12 over 2 squared minus 2 times 2. And this is just 4 plus 8 minus 12 over 4 minus 4. 4 plus 8 minus 12 is 0. 4 minus 4 is 0. So now we arrive at this thing, but we actually can't call it a number because remember, you can't divide a number by 0, right? The denominator can't be 0. So this is just undefined. But does that mean the limit is equal to this? So does that mean the limit is just undefined? Well, remember that the limit and then something like this, these are not always necessarily equal together. It's simply the condition that has to be true in order for us to use direct substitution. But we don't know if the limit actually does equal this or is undefined. We just know that f of 2 gives this output, right? So we can't jump to conclusions and automatically assume the limit is this. And in this case, here's where we will use a new tool, the idea of factoring. And what that does is we are going to try and simplify this. And in this case, factor this in an attempt to get another output. So what we will do is we will rewrite this right here by factoring it. And you might be able to see why in a second. So the top here is going to be x plus 6 times x minus 2. Right? If you double check it, it'll come out the same. And the bottom is x times x minus 2. So this is the same as this. And you can notice that these cancel out, right? And what's so important about these canceling out? Well, if you look at this carefully, x minus 2, this is the whole reason our output was undefined in the whole place. Because if you plug in 2 here, right here, 2 minus 2 is 0. And that makes the entire denominator 0, right? So now we're removing the entire possibility for this function to even be undefined. So now this will be x plus 6 over x. So now let's try direct substitution. Let's plug in 2, we get 8 over 2, which is 4. So we can see that, once again, this proves the idea that these two concepts aren't the same. The input and output of a function and the limit, they don't always have the same outputs, right? In this case, the limit is actually 4, and the output for this function is actually not a number. And this thing right here is actually, it has a name, and it's called indeterminate form. Indeterminate form. And this symbolizes that the function may not be defined, but that does not mean the limit is undefined either. This is simply a symbol that you might have to do further steps. The limit, the true value of the limit is actually hidden. You have to take more steps, use more tools to find that value. And in this case, we use the tool of factoring. We simplified the function, we removed the possibility of it being undefined and leading to indeterminate form, and we found out that the true value was actually 4. So whenever you come across indeterminate form, think, is there any way I can maybe use the tool of factoring to simplify the function? Alright, so now we have another example. The limit as x approaches 3 for x minus 3 over x squared plus x minus 12. And once again, especially if you're not experienced with solving limits, you might not know what tool to use, right? So that might be a big problem. How are you going to choose what tool you're going to use? Are you going to use direct substitution or factoring? The general rule is that you always use direct substitution first, because we know that in most cases direct substitution works, and it's the easiest, right? It's just plugging in numbers. So let's try direct substitution. Let's see what happens. So we have 3 minus 3, and then over 3 squared plus 3 minus 12. So the top is 0. 3 squared is 9, plus 3 is 12, minus 12 is 0. So you see, now we have the same indeterminate form, right? So that's a symbol that we have to simplify this function further to find the true value of the limit. So what we're going to do is we're going to simplify the function, and we're going to try and factor it. So the top really can't be factored, right? But the bottom has potential because it looks like a quadratic. So we know quadratics can usually be factored. Well, in a lot of cases it can. Let's see, maybe if I try -3 and +4, does that work? Okay, so it looks like this would work, right? If you expand this. So this would be the same thing as that. And now I can see that I'm now once again eliminating the entire thing that's making this function undefined. It's this x minus 3, right? Because if you plug in 3 here, 3 minus 3 is 0. It makes the entire denominator 0. So now the limit as x approaches 3, over, or for 1 over x plus 4 is our simplified version. Okay, so now let's try direct substitution. So it's just 3 plus 4, right? Just 1 over 7. So now we know that this is our true value. So now we have this example here. And you might see a trend here. Every single time, I'm just going to try direct substitution because I refuse to believe that direct substitution just immediately I refuse to assume that direct substitution does not work because how can I tell immediately, right? Unless you're very experienced. So I'm going to try it again. So I'm going to say that, I plug in 2 into the function, right? So I'm going to get 2 to the 4th plus 3 times 2 cubed minus 10 times 2 squared over 2 squared minus 2 times 2. 2 times 2 times 2 times 2 is 16. Plus 3 times 2 cubed is just 8. 3 times 8 is 24. 2 times 2 is 4. So 4 times 10 is 40. 2 squared is 4. And 2 times 2 is 4. Alright. 16 plus 24 is the same thing as 24 plus 6 plus 10. So 24 plus 6 is 30, plus 10 is 40, and 40 minus 40 is 0, and 4 minus 4 is 0. So this, once again, this is another symbol, right? It's undefined, so it's a symbol that maybe we have to simplify the function. Alright, so now let's try and simplify the function using factoring, because it seems a little obvious here because, you have these powers like x to the 4th, x cubed, x squared. That shows potential that maybe factoring is easy and maybe to some degree. So at the top, what can we factor out? Well, we can factor out x, but we can also do x squared. So let's try x squared. So x squared times, it will be x squared plus 3x minus 10, right? This times this is that, this times this is that, this times this is that. Okay. And now the bottom. So how can we factor out this? Well, the common factor would be x, it appears. So we pull out an x, and we get this. So let's check if this is right. X times x is x squared. X times -2 is -2x. Okay, so this is the same thing as this. It appears that we still will get indeterminate form because if you plug in 2 into here, that's 0, right? 2, 0. So the bottom is still 0. So the number will not be an actual number. So we have to keep simplifying. And we notice that we can maybe simplify this, right? This is not completely factored out. So let's factor that, see what happens. Oh, and why not cancel out this x, right? Because we can. And we're trying to simplify anyway. So let's do that first. Okay, so now we want to factor this. Let's see. What about 5 and -2? So x squared, -2x plus 5x is 3x. So that satisfies that. 5 times -2 is -10. So this would be correct. and then at the bottom we have x minus 2. And now, as I'm trying to simplify this, I see I can cross out that. Okay, so now we have this. And it doesn't look like we can really simplify this any further. So, because we can't simplify any further, we're going to try direct substitution again. And let's see. We get 2 times 2 plus 5. So this is just 7. So 2 times 7 is 14. So once again, we have a new we have arrived at the true value for the limit, rather than what the input of that function was, which was undefined, right? Okay, another example. Here, once again, the same pattern, the same steps. I'm going to try direct substitution first. I'm going to plug in 0 here. So I'm going to get 0 plus 6 squared minus 36 over 0. 6 squared is 36. So 36 minus 36 over 0 is 0 over 0. Okay, so indeterminate form again. Now I want to try factoring. So this is just the limit as x approaches 0. This is not immediate to how I could factor this. So maybe let's expand that first. So this expanding this would give us x squared plus 12x plus 36 minus 36. Right? Well, we don't really need that, but so we have this, and we can cancel that out. And before I try direct substitution, I'm going to simplify it further because just to be safe, right? And because I can. So at the top, if I factor this, I get x times x plus 12 and then over x, right? X times x is x squared, x times 12 is 12x. Okay, so now I'm going to cancel out another x here. Okay, now this looks like it's simplified. I don't think I can simplify this any further. So I'm going to try direct substitution. 0 plus 12. And that gives me 12. So here's one last example. And the steps are not any different from any of the past examples. It's the only difference maybe is that the algebra might be a little bit harder because this is a cubic equation. So we're going to try direct substitution. And I'm actually going to skip a step here. I'm just going to automatically tell you that this does lead to this thing right here, indeterminate form. So I'm not going to go through the steps of plugging that in. But what I am doing is, while I did skip the step, what you would do is to first try direct substitution like before, right? Plug in the -3 and you would get this. So that signifies that you need to try something else. Okay. So what we're going to do is we're going to try and factor this now. When it comes to cubic equations, common strategy is to separate these two. So something like that, where you would change the sign. You would attempt to simplify the top by factoring in two different places. So it would maybe be something like this. And the reason I did it this specific way is because I'm I'm trying to factor in such a way so that I have common factors here and here, x plus 3, right? So the bottom will just be x plus 3. And the reason this is so useful is because now I can rewrite this as x squared minus 6 times x plus 3, right? This gives to this because if you expand this, this is just x squared times this minus 6 times this, right? So now we can write x plus 3 at the bottom here. And we can see that we can cancel this out. So now it looks like our function is simplified and we can try direct substitution. So we get negative 3 times negative 3. Negative 3 squared is just 9 minus 6. And then 9 minus 6 is just 3. So hopefully these examples help to better explain how you would use the tool of factoring when it comes to calculating limits. But you also might wonder, when would I use this tool of factoring? Because as it turns out, there are other tools. For example, you already know direct substitution. And there are also other things that, or other limits and functions that can't be solved using factoring or direct substitution. So how would you know when to pick the tool of factoring specifically, right? You might have already noticed there are some indicators. For example, if you do have the limit as x approaches c for some function, if f of c gives indeterminate form, right? This number right here, that is an indicator that maybe you will have to use factoring. But it does not mean that you need to do it. It's just a sign that you might have to do it. Another sign is maybe if the function is like something over something, right? Because this whole indeterminate form is something over something, right? So if it's something over something, maybe that's another sign. And finally, if the function has some kind of, quadratic or maybe some kind of cubic form, right? Because as you noticed, all of the past examples, they had some kind of quadratic or cubic form, which made it a lot easier to factor them. So usually if it's something like that, it's another sign, once again, that maybe it's a good idea to use factoring as a tool.